Alright, hey everyone, welcome back, and we'll get started up with the next section. So, uniform acceleration is the next thing that we're going to cover, and basically start to move our way through understanding a little bit about how our speed works. We started off just talking about speed, which then changed into vectors with velocity and displacement, which then started to change into how this looks with graphing, and then start to talk about vectors in 2 dimensions. And so now we'll move into how acceleration kind of plays into all of this as well. So a little bit of terminology to start. Accelerated motion means non-uniform motion that involves change in an object's speed or its direction, or both. Whereas uniformly accelerated motion is motion that occurs when an object travels in a straight line and then changes its speed uniformly with time. So uniform motion basically means that it's a set rate, it's not changing. And whereas accelerated motion basically means that I have this change in speed. So there's a couple of graphs that are here, and you'll need either some graph paper or a ruler to be able to start to draw a Cartesian plane, an XY axis. And so it says use the table, we'll make 2 velocity time graphs. And so we have graph 1 and graph 2. We'll make our time axis our x-axis, and our speed, or our velocity here, it says traveling west, our y-axis. And so when you're making your scale for them, don't pick the numbers that you see right on the table. Pick a set scale like 1, 2, 5, 10, 20, something along the lines of that, where it'll show in terms if there's a change or something that we can be able to see clearly on your graph. So A then says what is the slope in this case, and B then says how are the graphs the same and how are they different. So take a second and just plot out the points, connect the dots together, draw a line, and come back when you're ready. Alright, so hopefully you've had a chance to draw those out. And so if I were to take a look at the graphs that are here, I've got graph 1 plotted out. That we have with the first set of points. So I've got our velocity axis on the side with the right units in meters per second. I've got our time axis on our x-axis in seconds, and then we're just going to plot out a couple of points to make this work. So I'm using my scale where every box is basically 4, something that's jumping 8, 16, 24, 32, 40, and using that to plot my numbers on the side. So at 0, 0, I'm going to put my first dot. And then at 1 second and then up 6, I'm going to put my next dot. At 2 seconds, I'm up to 12, so that'll let me put my next one in. Right here. At 3 seconds, I'm up to 18, so that'll be right here. And then at 4 seconds, I'm up to 24, and so right there. And so if I were to connect this together and draw a line going through these points, I should hopefully see this straight line start to pass through everything. Right, and really kind of give me a sense of where these are. So in this case, I have a steady increase in velocity. If we were to kind of understand what this graph is telling us, it's not saying that we're on cruise control here. We're not traveling at the same speed. We're changing our speed as time moves on. So in this case, really what we're doing is we're accelerating, right? We're picking up our speed as we start to move forward in time. So let's take a look at our second graph. Our second graph, I'm going to go through and do the same thing. So I've got 0, 1, 2, 3, 4 for my time, but this time I'm starting at 24 seconds at 0. So 0, 24, and then I'm moving my way downward, heading down to 4 and 0 down here. So at 1, I'm at 18, and at 2, I'm going to be at 12, and at 3, I'm going to be at 6. And so I can see here now what I have is a line heading downward. In this case, what's happening in this graph is I'm decreasing my speed as time moves on. And so if you think about, okay, if I can accelerate, then what's the opposite of acceleration? And hopefully you're thinking of the word deceleration. So I can slow down as time's moving on as well. So let's take a look and see what these mean in terms of these A and B questions. What's the slope in this case? Okay, so we can take a look at this and we can start to talk about, okay, what is the slope here? Well, the slope we just said was acceleration. The slope is saying this is how speed is changing over time. So we can figure out what this is going to be because we know how to do this rise over run stuff from before. We have a straight line. We can figure out the slope of it if we know 2 points on that line. And so just as a quick refresher, if I wanted to find slope, slope is basically rise over run, which is the change in y, so like a y2 minus y1 over x2 minus x1. So if I took any 2 points from my graph and plugged them into here, that would tell me what my slope is. So let's just take the first couple of points. We have a straight line here, or the first and the last point even. I'm going to take 0, 0, and I'm going to take 4 and 24. So 24.0 meters per second minus 0 meters per second. Okay, first point and last point over top of my x2 value, looks like it's 4 seconds, over top of 0 meters per second. So my slope here looks like it's 24 meters per second over 4 meters per second. So that looks like it's going to give me 6. And then this is really saying 6 what? In this case, it looks like it's meters per second. Oh, and I've got my units mixed up here on the bottom. Meters per second and seconds on the bottom. So when I start to figure out what the units are here, what's a meter per second per second? What does that mean? So maybe on the side somewhere over here, I'm just going to kind of doodle this in. Meters per second divided by seconds. Right? How do we handle division when we deal with fractions? And hopefully your thought is, okay, skip, flip, multiply, or you invert the second term and then multiply through. But basically this number is over 1. So we're going to flip that number and change this into a multiplication type question. And then we're going to multiply through. Meters times 1 is meters. Seconds times seconds is seconds squared. Meters per second squared. That looks like what we're going to have here for this unit. Okay, meters per second squared. So that's our slope. In this case, it was heading west. So if we're taking a look at our slope here, this slope is increasing, and I can see it right from the graph itself, right from the table even. I can see that this is jumping every single time by 6s. Right, so it makes sense because my time value is jumping by 1s, then I can take an easy comparison here to see what the slope is going to be. The same thing with graph 2. I can see that I'm jumping by single digits, by 1, 2, 3, and 4, and then the other one is decreasing, 24, 18, 12, 6. It's decreasing by 6 meters per second squared. So the slope in this one is going to be negative 6.0 meters per second squared. Okay, it's decreasing. How are the graphs the same? How are they different? Well, we just kind of mentioned one is increasing and one is decreasing. So one is accelerating and the other one is decelerating. One is speeding up, the other one is slowing down. How are they the same? Well, they're both involving velocity time graphs. So they're both kind of using the same metrics, so we can compare each one straightforward. But this would be an example of uniform motion. It's increasing its speed at a set rate each time. Its acceleration is uniform. So let's take a look at one more. Okay, graph 3. So pause the video, sketch out a graph for these ones, see what you end up with, and then when you're ready, come on back and we'll go through this one. All right, so velocity time graph for this third graph, this last one. We're going to go through here and we're going to start to plot some of these points out. So I've got 0, 0, I've got 1 and 10, I have 2 and 16. We have 3 and 20, so 3 and 20. And then we have 4 and 22. And so now if we were to take a look at this graph and I start to connect these together, it kind of looks like this curve shape that starts to happen. So basically it goes up and then starts to curve over, right, as it's moving. So how is this graph different than the first two? Well, the first two graphs both use straight lines. Okay, so the first two, they both had straight lines. And the idea behind this, and the key term here, is that they were uniform. Whereas graph 3, this one is non-uniform. Okay, so this graph is slowly changing its speed, but it's not in a predictable pattern per se. Like we kind of can figure out mathematically what this is going to be because it does follow a little bit of a sequence, but it's not just as straight as looking at the slope from beginning to end, because it will give me kind of a false metric in terms of what's happening here, more of an average than an overall value for each segment. So what is happening here then? If I were to take a look at this graph, it's still increasing its speed, but its speed is starting to lessen each time. So it looks like this one is speeding up to a point where then maybe it can turn on its cruise control and level itself out. Right? It's moving up to a set value, a set point. Okay, but it's non-uniform motion, non-uniform acceleration. Okay, its acceleration value is changing. So how does this all kind of apply to stuff that we're going to go through? That's the next section on finding acceleration.